Hello everyone, welcome to the fifth week of this course Microsensors and Nanosensors, and this is the first lecture of this fifth module where we are discussing humidity and some chemical sensors. So first of all we will discuss humidity, but before we discuss the actual humidity sensor, let us try to understand that what is humidity and why it is so important that we are discussing this in a lecture. So first of all, I just want to ask one question that why we should bother about humidity, okay? Why we are more concerned about this particular physical quantity and why we want to detect it at precise level, because we are discussing this under a course of electrical engineering. We want to have precision in its detection. Okay, so there are various applications of humidity sensors. First of all, let us try to understand those applications, then only we will be having sufficient motivation to study this. Okay, so first of all, these humidity sensors are very crucial in industrial processing. Okay, so humidity control in chemical gas purification is very much required. Okay, consider a gas cylinder which contains lot of moisture along with the say it's a domestic gas, for example, so it's a LPG cylinder. Okay, and it contains good amount of moisture. So in a 15 liter of say your LPG, there is say 500 ml of water, okay, or 500 ml of moisture. Okay, or say if you want to represent it in terms of gram per centimeter cube, or in terms of say milliliter per centimeter cube, okay, say 500 ml per centimeter cube. Okay, no one want that kind of cylinder in their household. Now if you go towards an industrial process where you want a very precise concentration of gases, say for example, if you talk about say ammonia, your cylinder should be say 99.99999, that kind of percentage in a fertilizer industry. Okay, so it is very important that whatever gas you are using is free from any moisture, or it doesn't have any humidity inside. Okay, so this humidity sensors are very much essential in gas purification. Okay, in dryers they are integral part. Okay, ovens be of any kind, okay, all these ovens have integrated humidity sensors. Okay, in the film desiccation it is very much important, because you want your film to be moisture or free from any moisture. Okay, then paper and textile production industry uses this humidity sensor heavily. Okay, and of course the food processing. Otherwise if the packaged food gain some moisture, okay, or gain some humidity, okay, or say if this packaging of this food, be it chips or be any other biscuit or any packaged food is being packaged in a humid condition, okay, it will not sustain even for a month. Okay, it will be destroyed, because we know that many bacteria can come at higher humidity conditions. Okay, so in industrial processing, humidity sensors are integral part. Okay, then for environmental control it is very essential. In the intelligent control of living environment in say buildings, particularly in the smart buildings, cooking control for microwave ovens and intelligent control of the laundry system, everywhere you will find these humidity sensors. Okay, in medical science this is very important, particularly for respiratory equipments, sterilizers, incubators. Okay, the pharma processing, be it packaging of a tablet or say manufacturing of the tablets. Okay, and of course with the preservation of biological samples and biological products, everywhere control of humidity is very essential. Okay, in agriculture it is also essential, particularly for the case of say greenhouse air conditioning, plantation protection, soil moisture monitoring, and cereal storage. Okay, we know that the warehouses where these cereals are stored, the condition of those rooms are prepared in such a way that the cereals can be stored for longer duration. Okay, and mostly this happened by controlling the humidity condition of those warehouses or storage. Okay. Other applications include manufacturing IC in semiconductor industry. Humidity or moisture level are constantly monitored in wafer processing. Okay. Apart from that, there are hundreds of application of these humidity sensors. Okay, you cannot imagine this industrial process without a humidity sensor. Okay, or even nowadays in your room, for your comfort and for other purposes, these humidity sensors have been utilized. Okay, so the ultimate the takeaway from this slide is the importance of humidity sensor is very high in case of industrial process, for day-to-day life, or for say agriculture purposes, or say for any other industry. Okay, so therefore monitoring humidity in precise level is very crucial. Okay, so before we understand the humidity sensor, let us understand the term humidity itself. Okay, so amount of water vapor in air can be understood by various ways. Okay, at least three ways we are going to discuss here. The first is absolute humidity. Okay, so water content in air at particular temperature expressed in gram per cubic meter is known as absolute humidity. Okay, so water content in air at particular temperature. So as the definition suggests, this definition is mostly absolute in nature. Okay, so total water content in air at some temperature. Okay, that temperature is fixed, but the what we are talking about is the water content in air. Okay, in particular volume, particularly they are expressed in gram per cubic meter. Okay, but there is another way to represent this humidity, that is known as relative humidity. We all are acquainted with this word, relative humidity, or RH. Okay, because if you check your mobile phone or any website which deals with humidity, it will say, you usually check that, okay, what is the humidity level of your present city, or if you are planning to go to another city, okay, you check the humidity. Usually you check the condition of humidity in that particular city. Okay, it give you several ideas, okay, of your visit. Okay, so relative humidity is a very crucial term, and usually it is most utilized term in case of this humidity. Okay, so it is the current absolute humidity relative to the maximum possible for that particular temperature. So as the definition suggests, it's kind of relative term. Okay, so it is the current absolute humidity. So it define the current absolute humidity with respect to the maximum that can be possible for that particular temperature. Okay, and usually it is represented by in percentage. So you can define it as current absolute humidity relative to the maximum for that temperature multiplied by 100. Okay, then there is one more way to define humidity, which is known as specific humidity. So specific humidity is the ratio of the water vapor content of the mixture to the total air content on a mass basis. Okay, so these are three humidities, definition of three different humidities used in industry. Okay, so in this course, particularly for next couple of lectures, we are going to discuss relative humidity and the sensors which can detect this relative humidity. Okay, so let us define this relative humidity in mathematical way. Okay, so percentage of RH is defined as the ratio of partial pressure of water vapor in the mixture to the equilibrium vapor pressure of water over a flat surface of the pure water, and that multiplied to 100. Okay, and of course this definition is valid for one particular temperature. So in this definition of percentage RH, where you define this pH2O as partial pressure of water vapor in the mixture, and this P star H2O as equilibrium vapor pressure of water over a flat surface of pure water. Okay, this definition is valid at one particular temperature. Okay, so this relative humidity become more contextual when you talk about humidex. Okay, so let us try to understand this humidex. You might have some of you might be knowing also what is humidex. It is basically a humidity index. Okay, so it is an index number to describe how hot the weather feels to the average person by combining the effect of heat and humidity. Okay, so mostly this humidex is used in the context of the weather conditions. Okay, so I have given one diagram. It is taken from this Tawakoli et al. Which was published in 2022. If you see this NOAA National Weather Service heat index, okay, say if the relative humidity is 40%, okay, and if the temperature is around 33 degrees Celsius, okay, it will feel you 34 degrees Celsius, okay, and it becomes even, you know, more distinguishable when the humidity is very high. Okay, now let us consider relative humidity of 90%, okay, and temperature is 33 degrees Celsius. So at 90% humidity, this will feel as 55 degree Celsius. So you can understand that temperature is 32 degrees Celsius. When humidity was 40%, the actual feel was 34 degrees Celsius. Okay. Now, when humidity has increased to 90%, okay, the actual feel is now 55 degrees Celsius, although the current temperature is only 32 degrees Celsius. Okay. So that's the effect of humidity, and that's why relative humidity is very crucial, okay, not only for environmental condition, for industrial processing also. Okay. So first off, first kind of device which were developed to measure this relative humidity was hygrometers. Okay, and in hygrometer, a psychrometer kind of device was very popular. Okay, in fact, it is even used nowadays also. Okay, it is not totally obsolete, but it is not that popular because of the rise of several electrical sensors. Okay, so let us quickly see what is this psychrometer before we actually define various kind of humidity sensor. Okay, so the psychrometers are basically, if you see this diagram, it contains two different thermometers. One is known as dry thermometers or dry bulb thermometers, and another is wet bulb thermometers. These thermometers are standard thermometers. It is not any special kind of thermometer or so. Okay, only difference is one thermometer contains this dry bulb and another thermometer contains this wet bulb. Okay, this wet bulb thermometer also have a cloth sock, okay, which is wet. Okay, now I am attaching this system, so I have two thermometer. One I am calling a dry bulb thermometer, another I am calling a wet bulb thermometer, and it is hinged to a handle. Okay, and this is rotated. Okay, this is rotated mostly for 30 seconds or say 40 seconds. Okay, in the ambient. Okay, now this was soaked before it is rotated. Now when you remove this, okay, there will be a temperature difference between this wet bulb thermometer and a dry bulb thermometer. Okay, now because some water was there which has evaporated when you have given some heat by rotating it. Okay, now consider that this wet bulb thermometer was having a temperature of 21 degrees Celsius and this dry bulb thermometer has a temperature of 25 degrees Celsius because there was no cloth soaked on this. Okay, so there is a temperature difference. Okay, and this temperature difference is used to calculate the partial pressure. So this equation that we have just now we have seen, this partial pressure of water vapor in the mixture divided by this equilibrium vapor pressure of water over a flat surface of pure water. This definition can be, or the variables of that definition can be found from this equation on which a psychrometer is based on. So usually the psychrometers come with psychrometer chart. Okay, so in that chart you will find that for a difference in this temperature there will be a humidity shown. Okay, so this chart is based on this particular equation where this PW is equal to PS minus PT into A into T wet minus T air. Okay, where this PW is the partial pressure of water vapor, PS is the saturation vapor pressure, Pt is the total vapor pressure, and A is the psychrometric constant, while this T wet and minus T air, or T wet is the temperature of this wet bulb thermometer, while T air is the dry bulb thermometer's temperature. Okay. So by this equation, these variables are calculated, and this chart gives you direct conversion of this temperature difference to some humidity percentage RH. Okay, and mostly this psychrometers are accurate. Okay, mostly you will find that around 5 to 7% RH difference is there from a electrical humidity sensor and this psychrometer. But advantage of this kind of humidity sensors are they are batteryless. If you see this complete diagram or complete structure of this psychrometer, battery is missing. So actually it doesn't require any external power supply. Okay, so in those conditions these psychrometers are still find its usability. Okay, so these are sometimes also known as sling psychrometers, and they are available in different size and shapes. Sometimes you will find that, as in this figure, as you can see, that these two thermometers are integral part of a strip. Okay, sometimes you will find that they are separate. I mean, it comes in a number of forms. Okay, so please note that in the say atmosphere, when it is rotated, drier the air is, cooler the wet bulb will be. Okay, and the temperature difference will be even higher. Okay, so that is the basic sling kind of psychrometers. Okay, but those are mechanical instruments, and they were discovered long back. But mostly we want a microchip kind of device to be integrated in a small system, and no, you do not have people to always rotate this by taking it outside and or so. Okay, and another problem with this kind of device is, if this wet bulb is not used for say 10-15 days, it is of no use. Okay, so you have to use it regularly, then it will have some lifetime. Okay, so with the modern era, different humidity sensor or RH sensors has evolved, particularly based on various transduction techniques. Okay, popular one out of this transduction techniques are optical humidity sensor, gravimetric humidity sensors, piezoresistive humidity sensor, magnetoelastic, capacitive and resistive humidity sensors. Okay, out of this, of course, the capacitive one dominates the market. Okay, with the presence of over 75% capture of this market, but optical humidity sensors are very accurate, and for applications where you want accurate applications, you use this optical humidity sensors. Okay, so this is pie chart where I have shown you that how optical humidity sensors based on different principles are acquiring the market. Okay, so mostly the research that are going on is dominated by absorption loss based optical humidity sensor and grating based humidity sensor, but then microresonators, interferometry, those kind of devices also exist. And what are these things? If you remember, a light can interact with a matter in various ways. Okay, so if I have a material which can interact with the say this is a material which can change its property when it comes in contact with humidity. Okay, when it comes in contact with humidity. Okay, particularly the property that I am talking about is the optical property. Okay, so we'll see that what is this absorption based humidity sensor, what is this grating based humidity sensor, what is this interferometry based humidity sensor and all. Okay, so the absorption based humidity sensors are those where water molecules absorb certain wavelength of light. Okay, so you have a setup where, say for example, this is setup where I am passing the light of intensity say I, and when there was no water molecule inside, I have an intensity I1. Okay, and when I have water molecule, the same light will be absorbed by this water molecule, say at some wavelength, say particularly say 3.6 micrometer light was there. Okay, it absorbs certain light. Okay, so this was a broadband light, it is absorbed at say 3.6 micron. Okay, so intensity earlier was I1, now the intensity will decrease for this particular wavelength, okay, and I have a intensity I2, okay. I may compare these things, okay, and I can find that what is the relative humidity, okay. Similarly, it is also, optical humidity sensor can also be developed based on refraction. Okay, so the bending of light as it passes through a medium with changing humidity can give you a refraction based humidity sensor. Okay, similarly, you can also develop reflection or scattering based humidity sensor where change in reflective properties or scattering of light happens due to the moisture. Okay, then you have advanced colorimetric kind of optical sensor which are categorized under fluorescence kind of devices where change in the light emitted by a material in response to humidity is detected. Okay, so there are various materials which shows this property, particularly if you see this cadmium telluride based system on gold. Okay, they have shown this some absorption properties with light. Okay, some plasmonic devices based on gold has been developed to possess this humidity sensing properties. You have some polymer based devices which can detect the bend loss. Okay, gratings are usually based on graphene oxide, some polyamides and carbon nanotubes. You have Fabry-Perret devices based on chitosan polymer as well as some hydrogels. Okay, you have microresonators based on reduced graphene oxide and polyvinyl alcohols. Okay, then two-path interferometry devices are very popular based on graphene oxide and polyvinyl alcohol. Okay, and there are other materials as like acrylic resin and some graphene oxide, modified some oxide like say TiO2, which has shown this absorption properties with moisture. Okay, so this is one example of optical humidity sensor which shows that photonic crystal hydrogel, which is developed by certain chemical processes, okay, they changes its color when it sees different humidity. Okay, say this is one example where you can see that under different humidity conditions, okay, the crystal color changes from a light gray to green from 50% RH to 90% RH, or even 20% RH to 100% RH when it becomes red in color. Okay, so this hydrogels changes its color when it is subjected to different moisture conditions. Okay, then you have fiber optic humidity sensor. They are based on this colorimetric interaction of the material. So those materials are immobilized on the surface of the fiber core or its cladding in the humidity sensing section. Okay, I will show you some example for that. Okay, in general there can be several mechanisms to study this optical sensor, but usually this humidity induced refractive index change in the materials are characterized. Okay, so this causes the transmitted optical intensity through the sensing section to vary. Okay, so when you have, say for example, this is an optical device. Okay, there is one material which is changing its refractive index when it comes in contact with the humidity. Okay, so once this light was passing when this material was not there, okay, or the material was there but it was not having any moisture inside. Okay, it has not absorbed anything. Okay, in the second case this material is there and it has absorbed some some humidity, say 40% RH or say 50% RH. Okay, now in the presence of this light, okay, there will be some some changes that can be detected based on what principle it operates. Okay, so usually these variations occur as a function of relative humidity depending on what material it is. Okay, this is one of the example where you can see that you have a moisture sensitive layer and a very good fiber core and fiber cladding. Okay, you have some input light at this fiber. Okay, and this I am calling as a sensing fiber. Okay, this is my reference fiber. Okay, this is my reference fiber. Okay, now you can imagine that a same light, okay, same light source I am using okay, and I have a, say, beam splitter kind of thing, okay. I have a beam splitter here, okay. So this is a beam splitter, okay. The same input is provided to this reference fiber system and to this sensing fiber system, okay. What happen is, you know, in this core cladding system, this input light passes and it is detected at this, detected by this spectrum analyzer, okay. Now say this is the signal that has been detected, okay. The same signal, say I am calling it S1, okay. The same signal S1 you can expect by this spectrum analyzer, okay, if this moisture sensitive layer has not absorbed any moisture, okay. Now since it has absorbed something, its refractive index changes. You know that in this system, this cladding has lower refractive index as compared to this core, okay. Now when I have altered the refractive index of this moisture sensing layer, where this layer is changing its refractive index with the absorption of humidity, okay. Now what happen when you are passing this light through this, okay, this light is going to propagate through this layer, okay, and you can detect a number of changes here. Number of changes means you can find change in the intensity. Since it is going here and coming here, it will of course take little more time, okay. So apart from intensity, you can also detect the change in time, okay. You can also detect change in phase, okay, and there are other ways also to characterize these changes, okay. And based on the standard calibration process, you can have this humidity displayed on this humidity sensor, okay. Similarly, there can be sensors based on absorption, okay. So I am giving you one example of humidity sensor which is based on absorption. You can see that I have a optical fiber, there is a probe, and I have this hot water and system where this is used to intensify the humid condition inside, okay. I have a standard hygrometer, okay. What happen when this humidity condition inside this chamber is altered, this probe will detect it, okay. This probe will detect it, and I have a helium neon laser, you know, which is passing this light to this fiber, okay. So say I have, say right now, say it is power meter, but it can be, say, simply a spectral analyzer or something else, depends on what principle you are using, okay. Now I have passed this light through this. In this probe area, this probe is nothing but a humidity sensitive material, all right. This is a humidity sensitive material. I am calling it probe because I am using it to sense this humidity, okay. Now this helium neon laser, monochromatic source of light, is passing through this, and I expect that under 0 humidity or 0% RH, okay, I should detect the power that I have delivered at this particular end, okay. I should detect the same power because this is a lossless optical fiber, okay. Now when this chamber is populated with the water molecules and the humidity, the RH value in this chamber is increased by evaporating this water, what will happen is, say, it from 0% RH, say it goes to, say, 70% RH, okay. This probe, you know, this probe will swell, because this is kind of polymer, okay. It is absorbing moisture from this chamber, okay. Now when this has swelled, okay, what is happening is you will find that the power meter that reads the initial power which is coming from this helium neon laser, okay, is decreased, okay, or depending on the probe, it can increase also, okay. Mostly it decreases, okay. This is one way. Second way is, say if this light is passing through this, there can be certain ways in which this light itself, you know, is absorbed by water molecules, okay. The light itself is the photons, you know, this laser is made up, I mean this light is nothing but packets of photons. This photons transfer its energy to this water molecules, okay. In the process what will happen is it loses some energy, okay. Then at this power meter, the power of this this light which was given by this monochromatic laser will also decrease, okay. So in both the conditions, the power read at this output has decreased. So this is another way, you know, to develop a optical humidity sensor based on absorption principle, okay. Then there can be other ways also to develop this humidity sensor. As I have mentioned, you can use simple grating techniques, interferometry, okay, and other principles of this optical devices to design these optical sensors, okay. So based on absorption, you have seen one example. Similarly, you can design other optical sensors based on reflection, absorption, you know, based on change in refractive index, based on reflection, then scattering, okay, a number of interferometry, okay. You can design a number of optical sensor. The principle remain more or less similar, okay. Now let us see some advantages of optical humidity sensors, okay. These optical humidity sensors are mostly have a very fast response, okay, because this has to do with the photons, okay. It has immunity to electromagnetic interferences, okay. Then this optical humidity sensors, because of the available you know lenses and other things, it can be miniaturized also. Nowadays handheld optical humidity sensors are also possible, okay. And there is a possibility of remote and distributed sensing using this optical humidity sensors, okay. The best advantage of this optical humidity sensors is that it can be used in any harsh conditions, okay. So in the harsh environment also these devices have potential to operate. However, these devices have certain disadvantages also, like it possesses a good amount of hysteresis. Typically this hysteresis is of the order of 1%, okay, which is not, you know, recommended in many industrial process, okay. Although it can be miniaturized, but even smaller devices is possible. So for in that context, it looks little bulky, okay. It require various lens systems and mirrors, which makes it bulky, okay. Then decontamination of these devices is possible, okay. If you are using it continuously, there can be instability that you can face, okay. Power consumption in these devices are very high, okay, because you have to operate the source, the detector, and if you are using this lens systems, okay, they may also require some kind of arrangements, okay, particularly for their movements, okay. For precise humidity measurement, some form of temperature compensation mechanism is required, okay. And lastly, these devices are costly, okay. So you need some alternate mechanisms or alternate transduction techniques based on which you can develop a more user friendly and more cost effective humidity sensor. So in the next lecture we will discuss some of those devices. Thank you.